Hey guys, I'm Pratish, and I'm going to talk about the basics of gravitational waves. We've all heard about LIGO's groundbreaking detection of these waves. However, you don't need to be a physics nerd to understand them, although you just might become one in the process. We'll start by creating water waves, to better understand waves in general. Let's go. So I'm going to drop this small rock into the pool. Let's see what happens. Ripples. Interesting. Let's try dropping the heavy ball now. Wow, we're definitely seeing a lot larger ripples there. How about I try throwing the ball in the water a little bit faster and let's see what happens. Wow, that was huge! Let's go back in and talk about it. So, we just made some waves. Let's look at the details, shall we? When the object is dropped into the water, it transfers its kinetic energy and momentum to the water molecules in its path, displacing them. Since water is a liquid, the molecules are so close together that they can't be compressed further by the object. Instead, they move upwards, forming waves. This is also why increasing the mass and speed of the object forms larger waves. Based on the equations below, increased mass and velocity result in the object having more energy and momentum, which is transferred to the water, enabling particles to move a larger upward distance. The result is that water molecules start oscillating up and down, moving energy away from the site of the collision. The areas where the water molecules are at their maximum displacement at the time are the crest of the wave, and the areas where the water molecules are at their minimum are the troughs. Eventually, the wave dies down, as the molecules lose their energy to friction and other resistance, gradually decreasing the amplitude to zero. In fact, all waves occur as a result of oscillations. The sound we hear comes from the oscillations of air molecules at certain frequencies, and all electromagnetic waves, including light, are formed by oscillations of perpendicular electric and magnetic fields, although we learn in quantum physics that light has both wave-like and particle-like properties. So what about gravitational waves? In order to talk about them, let's first watch a common but always interesting demonstration of general relativity. So, over here we can see a ball warping a blanket, or as general relativity would put it, a mass warping the fabric of space and time. Let's try with the basketball now. We can see that the increased mass causes a larger deformation, and we can also observe that, while the effect is more pronounced closer to the ball, it spreads throughout the fabric. This warping of space-time is a key part of general relativity. How about we see what happens when we oscillate a mass on the blanket? Or, in our analogy, let's oscillate a mass through space and time. Looks like we're observing ripples, propagating from the mass outwards to space and time. Let's try with a larger mass now. Yeah, we can definitely see that ripples are much larger now. How about we check to see if speed has anything to do with their size, like it did with the water waves? Seems like our hypothesis was right. The speed of the oscillations does correlate with the size of the ripples. As I'm sure most of you realize by now, those ripples were our representation of gravitational waves. They are caused by the acceleration of any mass, so even our little demonstration created actual gravitational waves. That's so awesome. So, why haven't we been able to detect gravitational waves before? After all, we routinely interact with electromagnetic waves, sound waves, and other types of waves. The thing is, gravity is the weakest of all four fundamental forces, so most gravitational waves, like the ones caused by me moving my lips right now, are nearly impossible to detect. We can only detect waves from the heaviest, most quickly accelerating objects in the universe. In fact, LIGO has only detected waves from merging/orbiting black holes, a system of two of the heaviest objects in the universe, weighing multiple solar masses, moving at almost the speed of light. As we saw, increasing the mass and acceleration of the objects increases the amplitude of the waves. That's why they could detect these waves despite the distance. How did LIGO do it? Well, the two tubes in this interferometer fire out a beam of light into a splitter that separates the waves into perpendicular directions, where they reflect off mirrors and recombine into a sensor. Normally, the returning waves cancel each other out, as the opposite amplitudes add and result in zero. However, a gravitational wave stretches and squeezes space into two perpendicular directions respectively. Since the speed of light stays constant, when the two waves finally combine, they have each traveled different distances and no longer perfectly cancel out. And this is a gravitational wave detection. We now understand the basics of gravitational waves and how they were detected, but why should we care? First of all, this gives physicists a whole new way to observe the universe and make discoveries. In fact, the only way to directly detect a black hole is by the gravitational waves it emits. Since gravitational waves can pass through matter unlike light, they may show us a whole new side to the universe. Also, gravitational waves may hold the key to the theory of everything. So far, physicists have succeeded in unifying three of the four fundamental forces. Only gravity has eluded them, since they are unable to unify general relativity with quantum physics. In quantum physics, all waves are particles, and vice versa. So if gravitational waves help find the theorized graviton, that could be a huge help in unifying gravity with the others, creating the theory of everything. I hope you enjoyed this video, and more importantly, enjoy the physics behind the explanations. Thanks for watching.